What's that? Okay.
E by dx equals h and d.
All right, it's gone far enough. Okay, no, okay. All right. Okay, we're ready to go then. Now, what we were just doing last time by finding dy dx at a point, and that sort of points you in the direction, that's the slope of the tangent line, so you can draw little tangent lines there. Oh, I thought you were just leaving it for me. Okay. While I've got you here, could I ask a favor of you? I didn't think about it until too late. Which is you? Which is the other one? Can you recognize your writing? That's you. Okay. I'll put it on top, so I'll know that's one. Okay, thank you. All right.
Till I go to grade them and mix up the order.
What's that?
Till I go to grade them and mix up the order.
Yes, then you'll be in serious trouble. Okay. All right. So what we were doing before with a differential equation, as long as it's first order, dy dx is equal to something, at any given point, you can figure out what that is, and you know that's the slope of the tangent line at that point. So to generalize the procedure just illustrated, the one we talked about last time, and we talked about the linearization of that point, okay? To generalize that procedure, we use the linearization of the unknown solution y of x at 1, y of x of equation 1, which, let me go write this down. Equation 1 was, okay, sorry, I can't breathe. Y prime is equal to sum f of x and y, okay? And you start with some y at some x0, not 0x, okay? Things aren't working too well. X sub 0 is equal to some y sub 0, okay? Yeah, okay? Now, yeah, or some value, any value, okay? And what that gives you is a point, so you plug that x0, y0 in here, figure out what that is, that's the slope of the tangent line at that point. And then from there you inch along and adjust, and that's basically Euler's method, okay? So, the linearization of this unknown solution, y of x, we don't know what y of x is, but the at x equals 0, that linearization, L of x, now, there's a part of me that wants to call it L of x 0, but no, this is actually a linearization of a variable x, is equal to, now, remember how we got what we did? Remember when you plug this in, that's your, when you plug x0, y0 in for f of it, x0, y0, that is now the slope at that point. Okay? So, say again? Right. So, from our y minus y1, except let's call it y0, equal to m times x minus x0, okay? Used to call that 1, but since they're calling zeros here, this is your m, f of x0, y0. That's the value of the function at some particular point. So that becomes, and then what you do is add the y0 to the other side. Okay. So the linearization becomes y0 plus f of x0, y0 times x minus x0. I know that looks messy, but that's... Huh?
L of x is y.
Yeah, your L of x is y. That's your linearization, your approximation of what y is, your linear approximation of what y is. Okay? So that's how we proceed with this. Okay? Now that's going to be the equation we live with for a while. Okay? Now,
It sounds like we have a better one coming along the way.
no, while we're doing Euler's method.
Oh, okay.
Yeah, that's what I meant. So,
You got me excited.
what's that?
You got me excited. There's a shortcut.
Right. No, hang on.
No shortcut.
Hang it up, yeah.
Yeah.
All right.
Thank you.
Now, given that first one, x0, y0, and we know we can calculate the slope, we know that slope at that point, and the linearization suggests to us what the next value might be, okay? Then, so the next value is then when your x becomes equal to the next value in line, which will be x1, which is x0 plus some small quantity h. Okay? As we're used to h approaching 0, you can sort of guess that's what we would be doing if we were going to do a limit of this. But we're just going to let it be some small h now. Okay? So then, that's your first approximation. Okay? And sorry. Your L then of x1, where it might be, would then be the y0 that you had from before, okay, plus f of x0, y0. Now, I really don't quite like the way they're doing this, times the x0 plus h, that's your x1 here, minus x0. Well, guess what? That is x0 minus x0, that adds a 0, so it's just times that incremental h that you have left. So basically, your y1, your next estimation, is your y0, which to me they should have gone straight to this, plus, no, they put the h in front, doesn't matter, h of, and then this would be x1, y1, okay? Now,
y1, shouldn't it be 0?
Or
no, you're saying for y1.
Yeah, right. Okay. In other words, get it in perspective. Okay. That's your linearization. That's what that. The top one is equation 1. The second is equation 2. Okay. To come up with what your next point is, the x1, you're given x0, y0. Okay, you know what it is. Calculate the slope, you have it. To get the next one, L of x1, which is going to be y1, is y0 plus, and because your x1 is x0 plus h, just a little bit beyond that, then it's going to be, and you see, in my mind, this should now be, this is the one you use to calculate what y1 is, okay, what your next approximation is. And then you multiply this, but suddenly this becomes 1 and 1 again. So what you do, you're given the x0, y0, you do this one time, okay? That gives you an approximation for what your y1 is, okay? You take, when you do this, that gives you an approximation for y1. When you plug in x1 here, which is x1 is that, so it's just an h, okay? So it's h times that. That gives you your y1. I think this should still be 0. So I'm trying to rationalize why they phrase it the way they do, and I just can't rationalize it. I think you have to calculate the y1 first, okay, from your f of x0, y0. I think they just moved that up to, I think this is still going to be 0, 0 here. And then once you calculated y1, then you do a y2 is equal to y1 plus h times f of x1, y1. I think that's how it has to be. Okay? Now, I wish I could show, well, you can see the figure there. The tangent line is going to project up and come up with a x1, y1 to be right there. The curve is turning up faster. The real x1, y of x1 will be up there, okay? This is going to give you a little bit of error, okay? Now, the key here and this is where I think it gets a little sloppy here, okay? Once you know I think we're almost going to have to, I think they've got their symbology a little screwed up. Maybe not, but it sure looks like it is to me. But they have two things going on here.
Well, I think they said equal y1 equal to the L of x1, right?
Yeah, it's approximately equal to. It's not equal to, but it's approximately equal to.
It's approximately equal to it, so they, I guess,
now,
fill in the blanks.
Yeah. And the L of x1 is approximately equal to this, but then they list it up here, L of x here, with that in there, and they list y1 with this in there, and it just doesn't seem like both of them can be met at the same time. But let's see if we can work through here. The y2 is equal to y1 plus h of f of x1, y1. Yeah, this is true. Okay, so what they have above, they have this and that together, which seems like that's wrong. But down here they have this right, this, and that, yeah. So this does look like, what I'm saying here I think is the way it's supposed to be.
So the Y2 looks more reasonable than the Y1 does.
Yeah, the Y2 is, I mean, they have that in the book, and my Y1 I think would have to be this, though they have it with X1, Y1 the second time they wrote it. I think it needed to be X0, Y0, because they had that over here, and then they changed the X1, Y1 there. I don't see how that could be happening, okay? So, this I think is the right method. I think they just, you see at the bottom of the page, that second Y1, one toward the right, Y0, H of f of X1, Y1, that's Y2. No, it's not either one. So they have a Y0 and then the other ones, they mix them up, okay? All right, Victor's here. Good deal. All right, we're at the bottom of page, just leaving the bottom of page 76, moving to the top of 77. Well, we've just moved to the top of 77. So basically, here is your recursive equation. I was trying to think what you call that. Y of n plus 1 is equal to y sub n plus h times f, yeah. Put a parentheses in the wrong place. Okay. H times f of x sub n, y sub n. Okay. We're in your h is a fixed increment. So your x sub n is equal to x sub 0 plus n h, in increments down the road, okay, where n is 0, 1, 2, 3, blah, 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 blah. Okay. And that procedure of using successive tangent line is called Euler's method. Okay. So let's do one. Hopefully it will be easier than all the blah, blah, blahs here. Okay. For some reason, okay, it's just not responding. Consider the initial value problem. And that's probably why it picks up the, well, I don't know. Initial value problem, y prime is equal to 0.1 times the square root of y plus 0.4 x squared. I think this is the one we used as an example earlier on the previous page, using the tangent line when we were talking about that, okay? And our initial value is y of 2 is equal to 4. I think that's the same as we used before, 2. Yes, right. Okay. Use Euler's method to obtain an approximation of y is equal to, of y of 2.5 using first h is equal to 0.1. Bless you. And then we'll do h is equal to 0.05. We'll do it twice, first with 0.1, then with 0.005. Okay? Okay. So this thing here is what we're calling our f of xy, right? And this is our initial point, 2, 4. Okay. So our recursive relation y to n plus 1 is equal to y sub n plus h times, and this is our f, this thing right here, 0.1 times the square root of y n plus 0.4 times x sub n squared. Okay? Okay. That's our recursive relationship. So we're going to start with h equal 0.1, and we're going to start the process. So, y1, okay, and we're going up to y of 2.5. We're looking for y at 2.5. Okay. So y1, which by the way is y of 2.1, right, because your x0 is 2, or 2.0. This would be y of, sorry, that was an n, y of 0, which was 4, plus, and what's your h? .1 times 0.1 times the square root of 4 plus 0.4 times 2 squared. Okay, which will be 4. So let's see what our y of 2.1 it would be. It would be 4 plus 0.1 times 0.2 plus, second? How did you get 4.4?
Oh, wait, it's not. I have plus there, sorry. That would be
1.6, right? Okay. Okay, so that approximation is 4 plus 0.1 times, huh? Say it again.
You're going to add them in.
Yeah, I'm going to add them out. I'm just
So that would be
carrying out in gory detail. That's 1.8, right?
1.8, and then that'd be 0.18.
So that would be 0.18. So this would be 4 plus 0.18, which would be 4.18. Okay, so there's your y at 2.1. Y at 2.2 is going to be 4.18, the last estimate, plus your 0.1 times, okay, what is your new x? That was, I'm sorry.
That's h. We got to put another 0.1 right there, right?
Yeah, the h is always 0.1, and I'm sorry, I got lost of what I was doing there. Okay.
So it should be 0.1.
So that's another 0.1, but this time it's the square root of 4.18, because that was our last y,
Right.
plus 0.4 times 2.1 squared. Okay, calculator time. I'm tired of doing these in my head. I can't do them in my head anymore. So I pull out the old calculators. And it happens to be that today I have one in here.
Oh.
So I think I'll use it. Okay? Boy, in my last class, someone used it, and I just erased the screen, but it was pretty pathetic looking. -1 plus 3. I thought, that's what you were using this calculator for, but never mind. Okay, 4.18 plus 0.1 times 0.18 onto the square root of 4.18.
I got 4.37.
You do? Is that what they got in the book?
I don't know.
Yeah, 4.376, blah, 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 blah. Okay, so they got that to be, and if you got it, that sounds close enough, 4.3768.
Yeah, 6845.
Okay, we'll stop there, okay? That's where they stopped. Okay, so y of 2.3 would be, they say to 2.5.
Oh.
Okay, 4.3768 plus 0.1 times 0.1 times the square root of 4.3768. And if you can do this on a calculator a little bit simpler. If I put that number in memory and then just call it up rather than having to type all those digits out, plus 0.4 times, and now it's 2.2 squared. Okay? All right.
All right, let's see what we'll do. Answer.
Yeah, I got a domain error. I must have hit something in wrong. Oops. Well. Okay. What you get?
4.59.
4.59.
13.
Yeah, they have 1.4. Okay. All right. Next, we'll do y of 2.4, and that would be that answer, 4.5914 plus 0.1. That's your h. And this happens to be another 0.1 because that was part of your problem. The f is that times the square root of the 4.5914 plus 0.4 times 2.3 squared. Okay. 4.5914 plus 1 times parentheses 1 times the square root of 4.5914.
I got one answer.
Say again?
It's a 4.8244.
Okay, let's see what the book got. 8244, got it. And one more time, this will be our y at 2.5. And that will be, plug that in, 4.8244 plus 0.1 times 0.1 times the square root of 4.8244 plus 0.4 times 2.4 squared. Six eight. Yeah, that's what they got. Okay. Now, see how that worked for 0.1, step of 0.1. Okay? Which is a fairly small step, not huge. I mean, not huge, but only took us 5 steps to get there. When we go to 0.05, notice what happens.
I'm guessing that you double the steps.
You're going to double the number of steps because you're doing half steps now. And so you're going to have twice as many calculations to make. And they come up with a little bit larger answer, 5.0997 as opposed to 5.0768. So it, huh?
What did they come up with?
Table 262 with H.
When they go by half steps?
By half steps.
Yeah.
Do you want to do that just to get the feel for it? I think you got enough feel for it last time.
Yeah,
but you see what you do. Now, only thing that changes here is this. That doesn't change. This becomes a 0.05, and that stays the same, and you plug in the same number there, that stays the same. All that is fixed, okay? And then, but then that's going to change your answer, so all the numbers that go in are going to be different.
So,
and, but you go in twice as many times.
It's kind of a...
What's that? Yeah. Well, actually, what you do is program a computer to do it, and then have it do, and it's much easier. All you do is assign that a value, and then plug that value, and then let it go.
You just take the original problem and multiply that by h, whatever your h is, and then add it to y plus the y and then.
Right. But your original one is your original xy, x here, y there, and with that h. And then after that, all your things have changed. Whatever that answer does, it goes in here, it goes in there, and this goes in there. And you do your operations again. But you see, rather than writing them down and punching them in on a calculator, just assign them a value. This would be y of an array of x of 1 through 10 or whatever it is for the next step, and y of 1 through 10. And once you have it going, you just the y of 2 would equal y of 1 plus 0.05, whatever the h is. That's just giving a value 2. H times 0.1 times square root of the y previous. Yeah, and you just do that. The computer does it, and then when it gets to the end, it stops. That's.
And so the answer here is 0.507 at that, or is it at each point you get that?
Okay, now what was the question again?
Kind of the solution would be y of 2.2 equals 4.37, and then do that for each one all the way to 2.5, or would it just be the 2.5?
Okay, what you're looking for is your approximation of y at 2.5. And with a small h, you get, with a 0.1 h, you get that. With a 0.05 h, you get 5.09. Not a huge difference there, okay? But then you haven't gone very far from where you started. You still don't know what the exact answer is because you can't come up with an exact answer of that equation. There's no, what you do is, technically what you would do is do this until you get to 2.5, and that gives you an answer. Then you start back again and take half of your h again, okay?
So 0.5.
Yeah. So, yeah, and then do 0.05 the first time, then 0.025 the next time. You just half the h, and then you send it back through the array again. You'll just have twice as many in the array every time and see what you come out. And after a while, you hope that this
converges on a point.
Yeah, I wanted to say converging. I'm not sure that's the right word, but it is. It gets closer and closer to a value, and you just keep you just every time you tell the computer to half the h and go through it again, and it has to take twice as long to do it the next time, and it keeps doing that until the difference between the previous time and the current time is within your tolerance. If you 0.001. Then set that as your limit, and when your y of 2.5 with an h of some value, and the next one you get no more than 0.001 different from what you had before, say stop. I'm convinced that's close enough. Okay, and that's typically how you run these things. Sorry. Yeah. So at some point, so now in example 2, we're going to do the same type thing, applying Euler's method to another one. This may be one we can solve. Let's take a look at it and see. Okay. Let's clear the page. Yeah. Okay. Consider the initial value problem y prime is equal to 0.2 xy with initial value y of 1 is equal to 1. Use Euler's method to obtain an approximation of y is equal to 1.5. So what we're looking for is y is equal to 1.5, and we're going to use h equals 0.1 and h equals 0.05. Okay. All right. This, remember, is your f of xy. Okay. So we're going to start with a y1. Yeah, y. Yeah, I was calling it y. Yuck. Y of 1.1. We know what y of 1 is. It's 1. Okay. So y of 1.1 will be 1 plus 0.1 times 0.2 times 1 times 1. Okay? Right. Okay? Right. This, yeah, I can do in my head here, this one. That would be 0.2 times 0.1 is 0.02, so that's 1.02. All right, good deal. So y of 1.2 then would be 1.02 plus 0.1 times 0.2 times 1.1, that's the x, times 1.02, that's your y, and see what that is. Okay? And that's a fairly easy multiplication to do because everything's just multiplied. Oops. Helps to turn on the computer. Helps to type it right. Huh? Okay. All right. Say it again.
1.04, we'll just shorthand it, but it can go further. It's
244. Okay. We'll leave it like that. We don't need that many digits. So y of 1.3 will be 1.0424. I'm going to stop there. Plus 0.1, that's your h, times 0.2. Yeah, that's part of the problem, 0.2. Okay, times 1.2 times 1.0424. Assuming they're stopping at 4 digits now. And we'll get that. Okay.
1.067.
1.067. One more.
5.
4. Round up to 5 or say it 4.
Round up. I got 4 5, so round up to 5.
Okay, well.
Oh, I plugged in the big long carry.
Oh, you did? Okay. Let's see if they did a yeah, here they did one. What did they get?
1.0675. This would be 1.3675. That's what they got.
Oh, I see it.
Yeah, 263.
1.0675. Yeah. Okay. Now, they may be doing this by computer and just rounding every time, but keeping all of the input. So you keep going like this. Y of 1.4 would then be 1.0675 plus 0.1 times 0.2 times 1.3 times 1.0675. And that would be 1 point. Is that what you get? 0.952, that's what they got. Okay, and then finally y of 1.5 would be 1.0952 plus 0.1 times 0.2 times 1.4 times 1.0952.
That is
1.1259. All right, that's what they got. Now, the good news here, the news here, is that we could actually solve this one exactly. Couldn't do the other one, but we can. So let's see what we get if we do that. That is dy dx is equal to 0.2xy. So what would you do? Yes, divide by y. And we don't say it that way, do we? Okay. Yes. Okay. So you have dy over y is equal to 0.2x dx. Integrate both sides. Okay. And this is the log of y is equal to 0.2 times x squared over 2, right? Which is 0.1. Okay. Right. Right. So y is equal to e to the 0.1 x squared. Okay? Now, we should have a constant in there, and that constant we could put the CE there, and then let's plug in our initial value. 1 is equal to C times e to the minus, e to the 0.1. Yeah. I can't read that even, so.
So 1 divided by C to the 0.1?
Right. Okay, so C is equal to e to the minus 0.1. All right.
0.904, blah, blah, blah.
Right, that sounds pretty reasonable. Okay, so all we have to do when x is equal to 1.1, you just plug in and use that value. I was about to sneeze, sorry. Hang off there for a minute. But anyway, you see your actual error is, the actual values are pretty close, especially if you don't stray too far from your initial point. But the further you stray, the greater your absolute error is, and also the relative error.
So what you're saying is the y of 1.1 is the 0.102 and it's actually 0.9 blah blah blah.
No, it's
The e to the negative 1.
no, it's, you plug that in. So y is equal to, what did you say that number was? 0.9048. Okay. E to the 0.1 x squared. Okay. So you plug in a 1.1 for x squared and do that manipulation. That's what the actual value is.
I'll give it a shot right quick.
Okay.
Just to see. And this is 1.02.
1.0212.
Yeah.
Yeah. See, that's what they got as the actual value. So your absolute value error, just a little bit away, is pretty small. Relative error, percent relative error, you go from what relative error is absolute. Let's see, is
To the hundredth place is negligible.
yeah. But you see, the further you get away, the greater the error is, and the reason is because you're going back to a wrong number to begin with, and it's getting wronger and wronger and wronger. You know, look that up in the dictionary. Now, if you go to 0.05 and do it, we could do that, but won't, unless you want to.
I mean, we got the basis of how to do it.
Right. It's just twice as many steps. But notice here, to get to your 1.5, you have an error of 0.37 rather than 0.0037 rather than 0.0073. So your percent relative error is half that of what you had before.
So the smaller the number you use,
the smaller the h, that means when you're getting your next approximation, you're doing a number much closer than what the real one is.
Yeah, it's just like before we had integration.
Yeah.
The smaller the columns,
Yeah, Riemann sums.
Yeah, the smaller
exactly.
the columns,
the closer you're getting to the real answer. And that's the same principle here too. But these, you never get the real answer because the first place, if there's any error, then you're using that error to calculate the next one. But if you have a small enough thing, you can limit the error to what it is. Okay. Now, what I was starting to say, and I guess I'll write it down on the screen. Victor, you don't have a book yet? Yeah, okay. They showed the absolute error, okay? The absolute error is these are absolute values now, that's where the absolute comes from, is your actual value, like the one we got from the real integration, minus your approximation. So that's your, that is your absolute error. Your relative error is then, okay, it's the actual minus approximate over actual, okay? And, or in other words, your approximate error, your absolute error over your actual value, okay? So it's that over that, and then the percent relative error is then take that thing and multiply it by 100 and make it a percent, okay? So that's how they came up with those numbers. Now, a caveat here. Euler's method is just one of many different methods in which a solution to a differential equation can be approximated. Although attractive for its simplicity, Euler's method is seldom used in serious calculations. So why do we spend our time doing this? Except just to show us how one such thing would work. We will go into greater detail in discussing numerical methods that give significantly greater accuracy, notably the fourth order Runge-Kutta method, referred to as RK4 in Chapter 9. And maybe we'll get that far. Okay? But the thing you were picking up on before, there are better methods than this, but this is a simple method.
Yes, I was thinking that.
Now, numerical solvers.
It just reminded me a lot of the Riemann sums.
What's that?
It reminded me a lot
Yeah,
of the Riemann
it really
sums.
did. But even earlier, when you were saying, oh, there's going to be something better coming later, there is, but it's much later, Chapter 9, which may be too later. Okay.
Yeah.
So, they go over here some computer programs that are called numerical solvers. And what they try to do is then pull back in. Now, sorry, let me approximate the graph. That is, we haven't told you what Runge-Kutta is. That's in Chapter 9, but what I think I'll do, oops,
Oh, wow.
okay.
Yeah, see, that's...
See, what Euler's method does, this was e to the 0.01 x squared. Okay, this is the actual function is f of x is equal to e to the 0.1 x squared. That's nothing we can actually calculate, do an integral for, okay? So Euler's method, I mean, the real thing is there, something like there, something like, let's see, punch in e squared.
7.38.
Yeah, 3, 4, 5, 6, 7, something up there. So here's what, ooh, no it isn't. That's e, e to the x. That's not e to the 0.1 x squared. Okay, let's erase that, sorry. Okay. All right. E to the 0 would be 1. Oops. E to the 0 is 1. Okay. E to the 0.1.
It just looks like a really big wide parabola.
Yeah. Well, not parabola, but yeah,
It's what it
exponential.
looks like.
Okay. So what is e to the 0.1?
That would be 1.1.
1.1. So something maybe like that. Okay. Then e to the 0.4.
I can give you better points. Like, when, see, you're doing x.
E to the
Equal
0.4.
2 is about 1.5.
1.5.
And 2, yeah.
Okay.
And
And e to 0.9. Yeah.
2.45, so about a little under 2.5.
Right.
4 is nearly 5.
Wait, 3, 4, 5. Nearly 5. Okay.
5 is like 12.
Okay. Off scale. So here is.
And it's actually continues on both sides.
Oh yeah, because it's squared. Yeah, so that's why it looks like that. We're only messing with this side. So there's the actual function, okay? Euler's method, I'm doing this for Victor's benefit, he doesn't have the book to look at, undershoots this something like this, okay? May not be exact, but something like that. Runge kutta, I have a hard time saying that. RK4 is a straight line approximation there, a straight line approximation there, straight line approximation there, straight line. So you see that it's not exact, but it stays pretty close to that. So much better, but a little more complicated.
It's just a lot like Riemann sums.
Right. Right, exactly. So, but it's a straight line approximation of a curve. So there's going to be places it's not very good. Okay. But, I mean, far better than Euler's.
Especially when there's a lot of curvature between 2 points.
Right, yeah. Okay. They also show here, using a numerical solver, when you get into the place where things aren't operating very well, and I'm not going into great detail here, but their graph here, and I'll try to draw it for Victor's benefit.
You probably just do a quick sketch.
Yeah. They do it in blue. This is a completely different function altogether. I don't even know what the function is, but it looks like it's something like this. And then all of a sudden shoots up and does something like this. Now, I don't know what that's trying to do, but it's sure not doing a very good job of it. Okay, so obviously numerical solutions have limitations. I can remember when I took the third numerical analysis course, the professor said, so you start getting close to maybe the real solution, but then the process really slows down. The closer you get, the slower it is to do, and you're still not getting close, but it takes them longer and longer not to get any much closer, In other words, they never actually converge. That's why I hated to use the term for converge, because they don't do a good job of that. So anyway, exercise 2.6, do number 1, 3, any of the odds 5 through 9, do 11, and think about 13. And if you had a computer algebra system, you could try 14, but I wouldn't. Then you have chapter 2 in review, and I think these odd numbers have their answers in the back, so you can pick out any of those you might want to do. 1 through 11, and this covers the whole chapter. 13, 15, or 17. Second? Yeah, oh yeah, just a second. Any of the odds 19 to 25, do 27, 29, 31, and or 33. Okay. So, before we go, is it time? Wow, how time flew when we were having so much fun. Always.
The next class is even more.
Okay, she hadn't copied it yet. That's right. I slid it under her door last night. Let me run down and get it. I'll be right back. And what I can do is stop